Hello. So today I'd like to talk about decoherence and the quantum to classical transition by Maximilian Schlosshaer. Schlosshaer's a physicist now at Portland, at the University of Portland, and he was, at the time of the writing of this, at about 2007, um, in Australia at the University of Melbourne. I believe he's German. The name might be a clue. So I picked up this book a long time ago. This may be the first book from the Frontiers collection I picked up. Somewhere in here I saw, yes, there we go, a receipt from Bay Street Coffee. I can barely read the Bay Street, that's faded out, but I can read the date quite clearly. So it was the 17th of January 2010, and that was somewhere in there. I'm not sure if that's when I started it or that's when I was at that point in the book. So I was just using this as a bookmark. Um, so this was probably the first time I read it. This would have been later on because if I was doing things this way, which I started doing while I was in New Orleans, um, several years after I left Fremont, California, when I was working for Western Digital, when I was working at Xavier, I started taking notes this way. And, there are a lot of them. This was a very huge book, um, or a very interesting book, especially since I hadn't looked at too many things in quantum foundations at that point. This book is about quantum foundations, and in particular, it's talking about decoherence and how it works in sort of quantum foundations in general. What are the basic things that go into quantum mechanics, and what do they really mean, right? Because people don't really know what they mean. And decoherence has been a pretty big effect in that, or has had a pretty big effect in that. What is decoherence? Well, I think the best thing to talk about decoherence is the double slit experiment, right? So with double slit experiment, what happens is you have interference between particles of light, um, in general. Um, Actually, I think he has some buckyball stuff going on in here, but you have interference between these particles of light. Just so you have interference just like you have in um, water waves. So if you have water waves that are coming in sort of sync onto a particular plane, you could notice that some places the waves interfere, in some places they don't, and that gives you some some interference bands. That's exactly what happens here. Maybe I should just run back down. Is it over here? So probably around here somewhere, though. Is it chapter 5? No, it's probably chapter 6. So probably somewhere in here you'll get interference fringes. So this is just intensity of the light. So that's, or these are for C70 molecules. So can I see that? I can. So you see these bands here. These bands are telling you that you have the interference. And I'm looking to see if there's a better looking one here. There isn't. So each of these bands are saying that in this area, the wave functions are canceling each other out. And in these areas, they're basically adding. So you get a large number of hits over here. You have a high probability of hitting in these bands that are barely visible. And you have no or very low probability of hitting outside of those bands. And this is basically the same experiment as for light, right? Except for this is with very large or I don't know if you'd call them macromolecules. But these are very large molecules. And because of that, we're seeing this over and over. They're making larger and larger molecules and, basically finding these effects. So it's very interesting. And that's something he's going to talk about in the book. So the basic idea would be you'd have like a laser doing that, and you get these interference effects. But you wouldn't get that with, just a regular old incandescent lamp or a even most diode um, white light sources. And that's because for one situation, for the coherent situation, you end up with sort of in phase photons, whereas the other doesn't. Now you're saying, hold on, Jim, what about Young? So when Thomas Young did his experiments in 1800, he was able to get these interference fringes. How was he able to do that? I mean, he just had some sort of white light source, right? And he did have a white light source, but there was only one really good white light source there. You couldn't do this with a gas lamp, right? It didn't have the intensity. You couldn't do this with a candle flame because it didn't have the. It's not stable enough to do these sorts of experiments. What he did was he had his lab in the basement. He had basically a tube that went through the entire building from, I don't remember how many floors, let's say the fourth floor down into the basement, and he reflected those things, and he used the sun as a source of coherent light to be able to do his interference experiments that were so important for the wave theory of light. So he was actually using a coherent source, which was the sun, which is almost as good as a laser. So the idea of decoherence is how do you transition from that highly correlated light to uncorrelated light? Now, one easy way is hitting something, right? So if you have this highly correlated light going through a dense gas, if you're going through like the fog or something like that, after your sunlight goes through the fog, it is no longer correlated because it's bounced off of so many things and it's interacted with the environment, and now your white light is turned into boring old incoherent light, right? The same thing with your laser. If you put your laser through a really dense gas rather than something dilute, you'll get a whole lot of reduction in the level of coherence. And we'll see that a little bit later in this book. So again, I really like this. It's part of the Frontiers collection, which is one of my favorites. I think this was my first book from the Frontiers collection, like I said. I should say that this had nothing to do with the name of the podcast, right? The podcast Physics Frontiers. We've talked a lot about things like this. I think, let me see, we had Wigner's Friend, and we had spooky action at a distance about some of these experiments they were doing in Geneva to, try to get rid of, arguments against why somehow something between two particles could actually talk to each other, with some sort of signaling less than the speed of light, which is sort of a problem. So people try to talk about things like, Bell's theorem that said we had to use these quantum probabilities and these quantum things rather than some detailed classical probability theory. People found lots of ways around it that aren't really meaningful, but there's like maybe this could happen, maybe that could happen. The experiments that Alain Aspect did, they aren't not they're not completely determinative. And every time somebody says that, somebody else goes and make an experiment and it says, "Oh no, quantum mechanics works," right, as advertised, and so forth and so on. So I don't want to get too much into that, but we've talked about some of the things that impinge on this, maybe, I don't know, maybe that are related to this several times. So yeah, let's go through the book. The book is not a textbook as such, so right, it doesn't have any problems or anything for you to do. this is really just for, reading and leisure, right? And I think we can find some really leisurely pages. That's a fairly leisurely page, but I saw some more leisurely pages. See, this is a pretty leisurely page here. This is the sort of thing that, will relax you and, you know, give you some things to talk about at parties. And this one randomly shows up, so I may as well talk about it. The reason why I'm talking about this is when I was going through my notes, I noticed that I was paying a lot of attention to this because when I read it, 10 years ago, because, here it says equation 3.83 is wrong, the second term under the radical. There's a problem here. And if you look at it, there is. Basically, there's a typo here. This C should be squared, this C in the second term. The denominator of the second term should be squared, BFD. But that was me looking at things. It's the same kind of observation that shows you're paying attention in class where the professor's doing some derivation or something, and you notice he forgot a 2 or something like that. That shows that you're paying a lot of attention, and you're paying especially attention to all of the trees and ignoring the forest that he's trying to get across altogether. Let's see. Sometimes when I'm looking at this, I feel the same way because there was a lot I missed on this. So when I go through the table of contents, I might be explaining a lot of things wrong, especially the way he thinks about them. So first we're introducing decoherence, and that actually starts, if you look at the chapter, he's starting to talk about Schrodinger's cat, which talks about the measurement problem in quantum mechanics, which is the biggest issue in quantum foundations. So basically, what is the wave function and how the hell do you get a measurement out of it? That's quantum foundations right there. If you understand both of those things, then you've solved it, and then people can stop worrying about quantum foundations. There might be some things on the side, but you'll have to sort of do that with other regular research. But quantum states, what are they? That's part 2, basic formalism of decoherence. And that's kind of hard to talk about. So you've got classical versus quantum states. Well, what's a classical state? Well, if you have a classical state of an individual particle, what you have is what is its position at some time and what is its velocity, and that's its state. Okay, well, you have something similar with quantum mechanics. You have a distribution of possible states, eigenstates in the position and the velocity, and you can end up with one or the other when you do a measurement, right? And actually, from that whole list of positions and actually momentum, not velocities, from that whole list, you can technically get a really determinative view on one of those things. The particle is at this point right here. If you know that, you don't know what speed it's going. Or you could say it's going in this direction at some speed. So then you know its momentum perfectly. Although there's a possibility for other ones in other places and stuff like that. So you do a measurement, you can extract some information about that the particle, that's one way to say it, or you can force the particle into a position or force the particle into a momentum. But that's another way to think about it. But if you do that, then all of the other states, both in position and in velocity, you don't really know anything about. You don't have a determinative state in that other spot. So you get to know one item of information out of all the possibilities. Not so good. But better than that, the problem is well, it's not a problem that, you can't know that it's there. It could be anywhere in there, and maybe it's less likely to be here than here, but you can get some other information out of that, right? So you could have gotten some other information. You only know so well where things are, and that means that you have a distribution in these other um, measurements as well. So you could theoretically have a 50% chance of knowing where something is, and then the 50% chance of knowing. It has to do with the spread, really, not the chances. So if you have a spread in the positions, you have a spread in the velocities, and so forth and so on. So that you have some idea, but basically these probabilities for finding one of these states, those are your states, or your state. Your state is a probability um, function. Actually, it's the amplitude that creates a probability function, which is another problem in quantum mechanics. And then, of course, there's one more kind of state, which would be a thermodynamic state, which says we've got these measurable things we call macro states, like what is the temperature, what is the pressure. Then we have these unmeasurable things we call microstates, which are where are all the particles and what are their velocities. So it's sort of a classical idea, what are all the particles and what are their velocities. Those things we can't really measure just because there are so many of them. And then we have the macro state, which is sort of an aggregate of them, right? The temperature is the mean molecular kinetic energy, right? So that means even though we can't figure out what the kinetic energy of each individual particle is, we can know the mean of them in some way, some sort of aggregate, and we can get other things like entropy out of that. And then you might want to know, well, how do we interpret those quantum states? Well, generally we introduce them probabilistically. We're saying that this quantum state has some probabilistic nature. And then we go to the ontological status of the quantum states. I just looked at this again, and I don't think it means what I want it to mean, right? So when I look at that, I'm starting to think of the psiontic versus psiepistemic distinction. I haven't really been too into that, but right now I'm reading some papers for a superdeterminism episode of Physics Frontiers, and yeah, I think that you have this question: is what does the wave function represent? Does it represent the actual object, or does it represent um, our knowledge of the object, right? And if it was really completely all about the object, if it was really the object, you'd have something like, I think Schrodinger, I'm not sure, somebody had, um, this idea of a mass wave, right? But it's not really that. That's not what it is. It has something to do with probabilities, right? And so, therefore, if it has something to do with probabilities, it probably has something to do with some kind of um, epistemic judgment about the world. The you know there are electrons, let's say, although people might say there aren't, but let's just pretend there are. And the electron has a wave function. Well, does it have a wave function? Does the electron actually have a wave function, or are we just imposing a wave function as the mathematical description of the electron's position because that's how it works out that we can actually measure it? And it seems a little more like the latter than the former. The electron does not have a wave function. We have a wave function that describes our knowledge about the electron. I don't want to get too much into that because that can also turn into mysticism. Okay, then we have a superposition principle. The superposition principle here is a little bit different than the superposition principle in electrodynamics. So the thing here is that the superpositions here that I'm seeing from him in 20 here, this is basically taking a total state and looking at it as a linear sum of its basis states is what it looks like to me. And that's fairly fine for a simple experiment, like the Stern-Gerlach experiment right there. So that tells us something about, we have multiple possible um, states, basis states that our system can be in, but there are, um, but the state of the wave function, the actual state, could be a linear combination of the states we could actually measure. Although when we measure, it's in one of those states, but the state of the wave function can be a linear combination of those states. Um, so that means if there's a possibility that it's up and it's a possibility that it's down, let's say there's also a possibility that our wave function has, let's say, half and half of each. It's not really that way, but let's say half and half, just to make it a little easier. Then we want to experimentally verify these superpositions and give a scope of the superposition principle. Now, the scope here is the interesting thing. So what Schlosshaer is talking about as far as the scope here is how big a thing has some sort of entanglement, right? How big a thing is in a superposition. And classically, if you were to talk to Bohr, for example, too many people with similar names, Bohr, Bohm, Born. Anyways, if you talk to Bohr, he would say, if you have a macroscopic object, that is described by classical mechanics, right? If you have a microscopic object, it's described by quantum mechanics. And so you can't apply quantum mechanics to the macroscopic object. But in general, macroscopic objects should be able to be described by quantum mechanics. The issue is going to be decoherence. But we're getting larger and larger things, and we can produce these interference experiments with them. Right? If, and this is a big if we can convince them not to interact with anything else in the world before we do the interference experiment. So you could take real kittens, right, and do interference experiments with real kittens if you could keep the kittens from interacting with anything. But that would be bad for the kittens, so we can't really do that. But technically, we probably could if we had a properly set up experiment, which you don't, right? And I don't know how we do it. I wouldn't say it's hard enough. I bet at this point, doing interference experiments with Buckyballs is nice and simple with C60 molecules. But we get to that a little bit later. Then we get into quantum entanglement, how the states can be, how states of two different things can be related to each other, right? This is kind of hard to set up, but it's something that should be happening all the time. Every time two things interact, you should end up with an entangled object. But most of the times that two things interact, there are more entanglements that happen very quickly, and so it becomes very difficult to actually couple two large objects through entanglement that way. Density matrices. Density matrices are another way to talk about quantum mechanics. The place I remember seeing them most, I think, are in sort of these quantum optics sort of books. I don't see them very often other places. But if you're going to talk about lots and lots of measurements and things like that, you're going to want to talk about density matrices. They're just another way to set up quantum mechanics, but the density matrix is a very powerful tool if you have to do calculations. Then we get to the measurement problem. Right? This is the main thing about quantum foundations is um, the measurement problem. We get an ideal quantum measurement. Let's see if he has a drawing here. Um, yeah, basically you have a system and an apparatus. They're both in states, and you have an interaction between them. You have to have an interaction. I think in some ways this is a little sparse. In other ways that I'd say it's at the right level. Right, it's at the right level for the description here. But if you want to really understand the measurement problem, I'd go with something like, or the ideal measurement. I'd go with von Neumann himself, or maybe Aronoff with quantum paradoxes or something like that. And then he goes through some of these problems in quantum foundations. Preferred basis, non-observability of interference and outcomes, right? So these are problems that he's going to talk about here. And those are 53 to 57. So we have these different problems that come up here, although they're basically related to the measurement problem, right? These are sub-problems of the measurement problem. Which path information and environmental monitoring, which sort of can destroy your interactions. But I mean, it's very interesting when you see these descriptions in weak field measurements. So there's a double slit experiment right there. Which path information? Oh, this is the which path information from that. I've actually seen that exact drawing in many places. I think. Well, I should say I think, but they end up being very, very similar. And so the question is can you detect which slit in that interference problem a particular buckyball goes through? So if you looked at that buckyball thing we looked at earlier, you'd noticed that it was all just there's the buckyball, all just little dots here, right? You can barely see them because they're little dots. I'm not sure how much you can tell. That's because you're really only seeing specific interactions. You see something very similar if you even look at like the original Stern-Gerlach information, because that came on a silver plate. You see the same sort of interaction thing with that. So the question is so the problem there is that you actually have self-interference, right? The interference is in the wave function. It's not between different things existing there, because only one of these things is going through there at a time. And you don't really get which path information. And the information and the environment can also destroy your interference because of that, right? Then we have pointer states and other things that I should have reread this before I talked about, but there we are. Quantum Darwinism, redundant encoding of information in the environment, and quantum Darwinism. Not sure, did I mention that Schlosshaer is doing stuff right now on quantum random number generators and quantum information theory? It's awesome, actually. I mean, if you read that, I do want to talk a little. I would like to talk a little bit about that. Maybe I will in the future. That's probably something I'd have to talk about myself. I'd have to read and talk about it myself on weekly electronic paper, or whatever I wanted to call it. I don't think Randy would want to talk about that. Let's see. Then we have a simple model for decoherence where we've got an object and an environment, and the object entangles with the environment a little bit, and that gives you your decoherence. And that's part of the reason why when you measure something you get a single state, is because you're interacting with the object. decoherence versus dissipation. So in these, in some of these sections, what he's doing is he's taking similar things that people sort of think of while they're looking at decoherence and saying how they're not that, right? How decoherence is not dissipation, right? Dissipation is energy loss to the environment, whereas decoherence is entanglement with the environment. It's a completely it doesn't include any energy loss. It might include some information loss, but doesn't include any energy loss. Classical noise. What is the difference between decoherence and classical noise? When you're buffeting things or buffeting things with buffeting things. Anyways, buffeting things with other things, right? When you have like quantum, when you have like um, Brownian motion, where you have like little things hitting this guy, and then my leather stuff falls down. But where you have something moving around in a random um, sort of path. Um, Virtual decoherence and quantum erasure. I sort of read that, and I'm still not interested in it. Resolution and into subsystems. So how can you break things into different subsystems? And this is where like the spooky action at a distance, he says, comes from. So what happens is we break the world into these subsystems, and you have one subsystem over here and one subsystem over here. Are they really broken up? We've drawn little imaginary borders on these subsystems, but why does nature care about where we draw those little borders, right? How well can we really take one large system of quantum particles and pull it apart for our analysis? To what level does that work? And so if it doesn't work very well, we get strange things like spooky action at a distance. Basically, if we draw those circles around subsystems in a poor way, um, we get non-intuitive ideas about what's happening with the world. Some formal tools. Some of these are really normal. Schmidt decomposition, everybody knows. Operator sum formalism, everybody knows. With the Wigner representation, that's like the density matrix except for continuous systems, and that's just talking about the basic formalism. Decoherence is everywhere, right? Particles are interacting with other particles all the time. This other book here, I shouldn't try to read a book that I read somewhere before, but this is a book on open quantum systems, and somewhere in here, and I was going to say it was at the very beginning, he's trying to talk about, well, we say that the wave function collapses during an observation, but in the real world, there are observations at any particular time. Now, obviously, there's the Bell um, question. Does an observation only count if somebody has a PhD in theoretical or PhD in physics to observe it, right? Um, what is the proper level of experimentation? That also goes with Wigner's friend, or proper level of observation. But if the observations are scattering events, if they are energy transfer events, then things are a little bit more interesting. Then he talks about a decoherence factor. That is, every time you have an interaction, you lose a little bit of that coherence with the system. So what is that decoherence factor, and how fast does it disrupt what you're doing? It talks about partial and which path resolution in these different limits, and talks about thermal photons and air molecules. That's really what we care about, right? This is the thing that's all over the place. We have thermal baths. We have these random photons that unlike the laser light, which every everything has the same phase, have random phases. Those virtual photons interact with things, and they interact with the and those other things interact with the other photons that are the coherent photons, and all these phases are all sort of randomized, and then you have incoherent light. Photon scattering air molecules, comparisons with experiments, and illustrating the dynamics of decoherence in 139. So let's go over there. I don't think this is where the actual interaction thing is. This is a scattering event. This is how we usually picture scattering, as something before and something after, right? Bam, that's it, right? And then we have a wave function for the thing that was scattered against. In the environment, you get a lot of these scattering events, which is why you end up with decoherence. And we're calculating the factor. I thought there was a plot over here that I liked. So you see what's happening with the coherence length. And if you have the environment in there, it dissipates really quickly. This is a logarithmic scale. I thought there was actually a plot. And I'm not seeing the plot that I wanted to see, so that plot was at some other spot. That plot was at some other spot. But you do have this decoherence factor that comes about, and I was hoping that the dynamics of decoherence would show that. Showed some other things, but it didn't show what I wanted to see. Master equation formalisms. The best thing here is that you have a Born-Markov master equation, obviously Born rule, Markov chains. Put them together, you get something very interesting. You end with non-Markovian dynamics, but it's very small. So very important, very interesting there. I'm not sure the importance. If you know the importance, there are comments. The world of spins and oscillators and canonical models of decoherence, quantum Brownian motion, the SpinBoson model, spin environment models. Spin environment models is basically what I was talking about previously. Spin boson, well, you're talking about basically a fermion and a boson interacting without tunneling. Born-Markov master equation back over here for that particular system. Very interesting things. Not the data part. The Buckyballs are the data part, right? Atoms in a cavity. Those were sort of the first oscillations in observing decoherence. Interferometry with the C70 atoms and the squids, superconducting quantum interference devices, and apparently Bose-Einstein condensates and quantum electromechanical systems is in there. I had an interesting QES, QEMS. I think he uses as a abbreviation, because somewhere in here I've got one of these things where I take the acronym that he's using and put it vertically. So I remembered that. But I want to look at the Buckyballs again, because the Buckyball experiments that he was showing show something very interesting, which is they show the interaction with the environment. They show the interaction with the... I'm hoping they show this. Here we go. So here's the interference fringes for just a basic C70 molecule. So it's not really a buckyball, it's C70, it's not C60. Why Zellinger decided to do it that way, I don't know. You'll have to ask him. I'm sure he'll love you if you send him an email. And asking something like that. Maybe you should just read the read the paper. It's paper 264 might actually explain that. But send him an email. I'm sure he'll be happy if he's still around. So here we have our interference at the position of the third grading, and here we see the interactions with collisions with a background gas and molecules observed in 268. So the background gas reduces how much you get, and it also reduces the interference pattern. So this is the visibility, the size basically of the interference pattern relative to the intensity. And that decreases here as you increase the pressure. So that basically shows that these interactions, or this supposedly shows these interactions are going to reduce your coherence between these different things. And even more interesting things that happen. So you see, here we had thermal photons, right? So the difference between thermal radiation, so the difference between C70 and a photon is that C70 is a molecule, it's matter, photon is a force. So the photon, you can't, irradiate photons with radiation because they're already radiation, basically, right? But you can do that here. So you can put 10 watts of photons, of thermal photons generated by a lamp or something like that. Probably not a lamp, probably a lamp. There's a particular kind of lamp that you'd use. And you can see that what's happening here is you're reducing that, you're reducing the visibility. Here's a laser. So that's it. Beyond the Buckyballs. So they're still calling C70 Buckyballs. I thought it was only 660. And other kinds of molecules doing the same thing. And here are estimates um, for interference patterns with other things. Very interesting. So that was observing it. Quantum computing. Like I said, he's doing quantum computing right now. He's doing interesting things with random number generators. So I don't see quantum random number generator here. So he wasn't thinking about this 15 years ago or whenever he was writing this. Maybe he was, but he didn't shove it in here for us to find out about. He was keeping it to himself then, right, until he figured it out. So an overview of quantum computing, decoherence, and some of the problems that you're going to have with decoherence in quantum computing versus classical fluctuations as well. Error correction, decoherence, free subspaces, things like that. Then we get into the role of decoherence in interpretations of quantum mechanics. So this would be another fun one. I mean, if Randy and I got together and wanted to finish up the quantum paradoxes, which I don't think he wants to do, then just like we used the list of interpretations here for a podcast, right? We used the list of interpretations that's in this book, which I don't remember. Did I do this book for you guys as a review? Probably. I like that book. Maybe we could go through here. So this has, Schlosshaer has his description of these things, Copenhagen interpretations, relative state interpretations, which he thinks are very much like decoherence. Those are the ones I think he likes best. Those have Everett branches, so these are like many worlds things, and things like that. Modal things. I know a lot more about this than when I read this, so I probably should reread these for some other things. Physical collapse theories, right, which gives you that preferred basis problem again. And Bohmian mechanics, particles and trajectories, and the summary. Now, I think if I remember right, the summary here, I mean, this is a really great chapter. If I remember correctly, I think the end product here was decoherence doesn't really solve the problem. Some people, especially at this time, and I'm not sure if they still do, but some people think that this does solve that problem. Oh crap! I hope this is. I'll have to check again when I go through this. Um, Hopefully, did I zone out for a while? I'll have to check. um, my screen just blanked out, so hopefully I didn't um, blank out. So how long have I been doing this? For 50 years? I'm not sure. I guess that means it's time to wrap up anyway, because I'm going to have to go through there. But anyways, if in case you missed it, good chapter on decoherence, on interpretations of quantum mechanics. Summary, I think what he says, if I remember correctly, is that decoherence doesn't really solve the problems with the interpretation of quantum mechanics. I have to go through and reread it again. Finally, observations, the quantum brain and decoherence. Quantum brain as a computer. I don't really like that. Anyways, the role of the observer in quantum mechanics. What is that really? How does that work out? What does he say? I should have looked at that. Collapse chain von Neumann. Okay. I'm not sure what this is. Page 378. Oh, I should mention this. I didn't remember this. He does say in 8.6 here, adding decoherence can make otherwise problematic interpretations tenable. So actually, according to what I wrote here from his notes, from my notes reading this previously, then it actually makes things worse for quantum interpretations. So it doesn't just not get rid of interpretations, it makes it harder to get rid of interpretations. And okay, so I'm good. So I'm looking here. Brain, basically, he's saying the brain is not a quantum computer. The brain synaptic connections have a large fail rate, even higher than the quantum fluctuations would give you. Decoherence is required for these subjective um, interpretations of quantum mechanics, like these guys. So that is that. Let's look at that uh, appendix and see if it's anything interesting. No, okay. Then I will let you go. This is, he has a review of modern physics article. Okay, so this is Maximilian Schlosshaer's book. Very nice. Um, that's his head right there. He looks better now. And like I said, I did like this a lot when I read it a long time ago. I think you should consider it if you like quantum foundations, and a reasonably tractable book on uh, quantum decoherence. There are a couple of places where you get a lot of physics or a lot of equations, and there are a lot of places where you have hardly any. So I think if you you don't just have a heart attack every time you see a differential equation, then you'll be happy with this book. If you want to learn a little bit about decoherence. Um, I don't remember if I mentioned it, but I do like the Frontiers collection, but that's not the reason why we named the podcast Physics Frontiers. That was just Randy really liked the name, and even though I tried to get away from it because we've got the Frontiers collection, we have Frontiers in Physics. I think that's also a Springer book, and there are Physics Frontier Centers from the National Science Foundation. I thought it was overused, but apparently it's, we've got a lot of people listening these days, so probably it was not a bad idea. So, anyways, here is what I was just talking about. Maximilian Schlosshaer, Decoherence, and the Quantum to Classical Transition. Good book. Maybe I should do it this way so you can actually see the thumb. So check it out if you'd like to. Also, really great series. Some of them are better than others, unfortunately. But just look at some of these titles here, right? A whole book on quantum superposition, symmetry rules. I think Schlosshaer has done a much newer book on. He edited a book where he was interviewing physicists about. I think it was him doing the interviews about interpretations of quantum mechanics and stuff like that. So, very interesting series, very interesting book, and thank you very much for listening. And I will hopefully have another book ready for you next week. Bye now.